for a moment, what I need to do is project something on the screen of your imagination. We're in 17th century Japan on the West Coast, and a little wizened monk is hurrying along near midnight to the crest of a small hill. He arrives on the small hill dripping with water. He stands there and he looks across at the island Sado, and he scans across the ocean and he looks at the sky. And he says to himself very quietly, Arayumiya, Sado ni Yokoto, Ama no Kawa. Basho was a brilliant man. He said more with less than any human that I have ever read or talked to. Basho, in 17 syllables, juxtaposed a turbulent ocean driven by a storm now past and captured the almost impossible beauty of our home galaxy with millions of stars, probably hundreds and hundreds, who knows how many planets, maybe even an ocean that we will probably call Sylvia in time coming. As he was nearing his death, his disciples and followers kept asking him, what's the secret? How can you make haiku poems so beautiful, so easily? And toward the end he said, if you would know the pine tree, go to the pine tree. That was it. Sylvia has said we must use every capacity we have in order to know the oceans. If we would know the oceans, we must go to the oceans. And what I'd like to talk to you today about a little bit is really transforming the relationship or the interplay between humans and oceans with a new capability that is not at all routine yet. I hope it will be. There are a few key points. One of them is the oceans are central to the quality of life on Earth. Another is that there are bold new ways of studying oceans that we have not used well yet. And the last is that these bold new ways that we are exploring as a community will transform the way we look at our planet, our oceans, and eventually how we manage probably the entire planet, for what it's worth. So what scientists do when they begin is to start with the system. They define what the system is. The system isn't Chesapeake Bay. It's not the Kuril Arc. It's not even the entire Pacific. It's the whole planet. The entire planet, continents and oceans together. That's the system. And basically our challenge is to optimize the benefits and mitigate the risks of living on a planet that's driven by only two processes, two sources of energy, one of which is solar. It drives the winds, the waves, the clouds, the storms, and photosynthesis. The second one is internal energy, and these two war against one another almost continuously. Mountain ranges, plate tectonics moves the continents around, forms ore deposits, volcanoes erupt. That's the planet that we live on. It's immensely complex. Now, I don't expect all of you to see all the details here, but what I want you to see is this is about 10% of the processes that operate within the oceans almost continuously and have for the last 4 billion years. This is a system that's been around a very long time, and these have all co-evolved. What do I mean by that? They interact with one another constantly. All of them interact with one another. So the complexity of this system that we're looking at, the one driven by the sun, upper portion mostly, and the lower portion is partly driven by the input from heat below and by other processes. This is very, very important because this is the system, this is the crucible out of which life on the planet came, and it's now time for us to understand it. We must understand it. That's one of the themes that Sylvia reminds us about. Understand this ocean of ours, this basic life support system, the dominant life support system on the planet. Look at this complexity here. This is only one variable. If you can see the complexity, you can see how tiny little eddies and large eddies and the motion, this is just sea surface temperature, but it's immensely complicated. Now layer in the other 200 or 300 processes that are all interacting, partly as a function of temperature, partly as a function of all the other factors, and you've got a really complicated system. That's our challenge, is to understand this system in new and phenomenal ways. And there's an urgency to this. Part of the urgency comes from the fact that of order, 1 billion people on the planet currently are undernourished or starving. And part of the issue is for Cody, who is here, 16 years old, and I have permission to relay this number, when he, 40 years from now, is the age of Nancy Brown, there are going to be another 2.5 billion people on the planet. We can't solve all the problems by looking only at the oceans. But if we don't understand the fundamental life support system of this planet much more thoroughly than we do now, then the stresses that we will face and that Cody will face, and even Nancy, who's going to live till she's 98, will have real problems coping. All right, let's talk about another perspective on the importance of the oceans. Look at this diagram, which is showing warm waters in red, cool waters in blue, and on the continents, what you're seeing in bright green is the growth of vegetation, and in olive green, the dieback of vegetation. And in the lower left-hand corner, there's a clock ticking away from 1982 to 1998, and then cycling again. What you'll see is that the rhythms of growth of vegetation, a subset of which is food, on the continents, is directly tied to the rhythms of the sea surface temperatures. The oceans control, or at least significantly influence, correlate with the growth patterns and the drought patterns and the rain patterns on the continents. So people in Kansas, in a wheat field in Kansas, need to understand that the oceans are central to them as well. Another complexity. This is the age of the oceans. I'm going to layer in on top of this the tectonic plates. The age of the ocean, the tectonic plates, gives rise to a totally new phenomenon that we have heard about in this conference. And I share with you some very high definition video that we collected in real time, seconds after this video was taken. People in Beijing, people in Sydney, people in Amsterdam, people in Washington, D.C. were watching it. Now, you've heard of hydrothermal vents, but the other discovery is that deep below the sea floor, there is a vast reservoir of microbial activity, which we have only just discovered and we have almost no way to study. Some people have estimated that the biomass tied up in these microbes living in the pores and the cracks of the sea floor and below rival the total amount of living biomass at the surface of the planet. It's an astonishing insight. And we have only found out about this recently. This is very, very exciting. It may be the next rainforest in terms of pharmaceuticals. We know little or nothing about it. Well, Marcel Proust has this wonderful saying that the real voyage of discovery consists not so much in seeking new territory, but possibly in having new sets of eyes, new ways of seeing things, a new mindset. And many of you remember the early stages of oceanography when we had to use what we had at our fingertips. And it wasn't easy. It wasn't easy in those days. Some of you remember this, I'm sure. And now we have an entire suite of tools that are really pretty powerful. Ships, satellites, moorings. But they don't quite cut it. They don't quite give us what we need. And the program that I wanted to talk to you about just a little bit here was funded, and it involves autonomous vehicles like the one running across the base of this image. Modeling, on the right-hand side, there's a very complex computational model On the left-hand side is a new type of mooring, which I'll show you in just a second. And on the basis of several points, the oceans are complex and they're central to the life on Earth. They are changing rapidly but not predictably, and the models that we need to predict the future do not have enough data to refine them. The computational power is amazing, but without data, those models will never, ever be predictive, and that's what we really need. For a variety of reasons, they're dangerous, but we feel that OOI, this Ocean Observatory Initiative, which the National Science Foundation has begun to fund, has the potential to really transform things. And the goal of the program is to launch an era of scientific discovery and understanding across and within the ocean basins, utilizing widely accessible, interactive telepresence. It's a new world. We will be present throughout the volume of the ocean at will, communicating in real time. And this is what the system involves: a number of sites in the southern hemisphere, shown in those circles. And in the northern hemisphere, there are 4 sites. I won't talk a lot about most of them right here, but the one on the west coast that's in the box is called the regional scale nodes. It was once called Neptune. And let me show you what's behind it. Fiber, next generation way of communicating. You can see the copper tips on these things. You can transmit power, but the bandwidth is in those tiny little threads smaller than the hair on your head in diameter, and this particular set here can transmit something of the order of 3 to 5 terabits per second. This is phenomenal bandwidth. And this is what the planet looks like. We are already laced up as if we're in a fiber optic corset, if you like. This is what it looks like, and the cables go really continent to continent. It's a very powerful system, and most of our communication consists of it. So this is the system that I'm talking about. Off the west coast is coincident with the tectonic plate, the Juan de Fuca tectonic plate, and it's going to deliver abundant power and unprecedented bandwidth across this entire volume in the ocean, overlying ocean, on the seafloor, and below the seafloor. Bandwidth and power and a wide variety of processes that will be operating. This is what one of those primary nodes looks like, and it's like a substation with power and bandwidth that can spread out over an area the size of Seattle. And the kind of science that can be done will be determined by a variety of scientists that want to be involved and can bring the instrumentation to the table. They will bring it and link it in. It'll be like, in a sense, like having time on a telescope, except you'll have your own port. Climate change, ocean acidification, dissolved oxygen, carbon cycle, coastal upwelling, fishing dynamics, the full spectrum of both earth science and ocean science simultaneously in the same volume. So anyone coming along later simply accesses the database and can draw down the information they need about anything that has taken place. And this is just the first of these. This is in conjunction with our Canadian colleagues, we've set this up. Now, I want to take you into the caldera. On the left-hand side there is a large volcano called axial seamount, and we're going to go down into the axial seamount using animation. Here's what this system is going to look like that we are funded to build at this point. Very powerful. That's an elevator that's constantly moving up and down, but it can be controlled by the folks on land who are responsible for it. Or they can transfer control to someone in India or China who can take over for a while, because it's all going to be directly connected through the internet. There'll be massive amounts of data flowing ashore, all available to anyone who has any interest in using it. This is going to be much more powerful than having a single ship in a single location and then move to a new location. We're flying across the caldera floor. There's a number of robotic systems. There's cameras that can be turned on and off at your will, if those are your experiments. The kinds of systems that will be down there, the kinds of instruments that will be on the seafloor, consist of, if you can read them there's cameras, there's pressure sensors, fluorometers, there's seismometers. It's a full spectrum of tools. Now, that mound right there actually looks like this. This is what it actually looks like. And this is the kind of activity that we can see with high-definition video, because the bandwidth of these cables is so huge that we could have 5 to 10 stereo HD systems running continuously, and again directed through robotic techniques from land. Very, very powerful. And these are the things that we're funded to do today. So what can we actually do tomorrow? We're about to ride the wave of technological opportunity. There are emergent technologies throughout the field around oceanography, which we will incorporate into oceanography, and through that convergence, we will transform oceanography into something even more magical. Robotic systems are just incredible these days. Absolutely incredible. And we will be bringing robotics of all sorts into the ocean. Nanotechnology, this is a small generator. It's smaller than a postage stamp, and it can generate power just by being attached to your shirt as you move. Just as you move, it generates power. There are many kinds of things that can be used in the ocean continuously. Imaging, many of you know a good deal more about this type of thing than I, but stereo imaging at 4 times the definition that we have in HD will be routine within 5 years. And this is the magic one. As a result of the human genome process, we are in a situation where events that take place in the ocean, like an erupting volcano or something of that sort, can actually be sampled. We pump the fluid through one of these systems, and we press the button, and it's analyzed for the genomic character, and that's transmitted back to land immediately. So in the volume of the ocean, we will know not just the physics and the chemistry, but the base of the food chain will be transparent to us with data on a continuous basis. Grid computing. The power of grid computers is going to be just amazing here. We will soon be using grid computing to do pretty much everything, like digest the data and everything that goes with the data. The power generation will come from the ocean itself, and the next generation fiber will be simply magic. It's far beyond what we currently have. So the presence of the power and the bandwidth in the environment will allow all of these new technologies to converge in a manner that is just unprecedented. So within 5 to 7 years, I see us having a capacity to be completely present throughout the ocean and have all of that connected to the internet so we can reach many, many folks. Delivering the power and the bandwidth into the ocean will dramatically accelerate adaptation. Here's an example. When earthquakes take place, massive amounts of these new microbes we've never seen before come out of the sea floor. We have a way of addressing that, a new way of addressing that. We've determined from the earthquake activity that you're seeing here that the top of that volcano is erupting. So we deploy the troops. But what are the troops? The troops are the autonomous vehicles, of course. And they fly into the erupting volcano. They sample the fluids coming out of the sea floor during the eruption, which have the microbes that have never been to the surface of the planet before. They eject it to the surface where it floats and is picked up by an autonomous airplane, and it's brought back to the laboratory within 24 hours of the eruption. This is doable. All the pieces are there. A laboratory. Many of you heard what happened on 9/7. Some doctors in New York City removed the gallbladder of a woman in France. We could do work on the seafloor that would be stunning, and it would be on live TV if we have interesting things to show. So we can bring an entirely new telepresence to the world throughout the ocean. This, I've shown you seafloor, but so the goal here is real-time interaction with the oceans from anywhere on Earth. It's going to be amazing. And as I go here, I just want to show you what we can bring into classrooms, and indeed what we can bring into your pocket. Many of you don't think of this yet, but the ocean will be in your pocket. It won't be long. It won't be long. So let me leave you then with a few words from another poet, if you'll forgive me. In 1943, T.S. Eliot wrote the 4 quartets. He won the Nobel Prize for Literature in 1948. In Little Gidding, he says, speaking, I think, for the human race, but certainly for the TED Conference in Sylvia, we shall not cease from exploration. And the end of all our exploring will be to arrive where we started and know the place for the first time. Arrive through the unknown, remembered gate, where the last of earth left to discover is that which was the beginning. At the source of the longest river, the voice of a hidden waterfall, not known because not looked for, but heard, half heard, in the stillness beneath the waves of the sea. Thank you.